So now let us discuss about the performance characteristics of measuring devices. So each and every measurement devices has got mainly two types of performance characteristics. First one is static characteristics and the other one is dynamic characteristics. So what is static characteristics? So static characteristics refer to the characteristics of the system when the input is either held constant or varying very slowly. The items that can be classified under the heading static characteristics are as follows. So the static characteristics means we are assuming that the input is either constant or is varying very slowly. So the characteristics of the instrument under such conditions are classified under static characteristics. Then dynamic characteristics just opposite of this, that is the instrument or the measurement characteristics are changing very fastly and frequently. So the characteristics become different under such conditions, and that is coming under dynamic characteristics. So these are the two types of performance characteristics of any measuring device. So first let us see what are different types of static characteristics. So these are classified as follows. So repeatability and reproducibility. Repeatability and reproducibility, that is RR studies, evaluate the precision of measurement system. It is important that the instrument properly calibrated before starting RR study. So that is how much repeatability and how much repeatability is there for an instrument. So we know what is repeatability. So that is the ability of an instrument to give the same output again and again when the measurement is taken at different times over a short period of time, provided the instrument conditions should be same. The same instrument and observer should be used, the same location, the same conditions are used throughout. So that is repeatability, the ability of an instrument to give the same reading again and again when the measurement is taken at short period of time under the same measurement conditions. Then reproducibility. Reproducibility describes the closeness of output readings for the same input when there are changes in the method of measurement, observer, measuring instrument, location, conditions of use and time of measurement. That is the ability of an instrument to give the same readings when the measurement is taken at different conditions, using different methods, then at different locations, different times, etc. That is reproducibility. So these are called RR characteristics. So this RR characteristics is very important from the measurement point of view. So next one is sensitivity. So sensitivity is the smallest amount of difference in quantity that will change the instrument reading. That is the minimum amount of input required to produce an amount of output or a deviation in the output. That is sensitivity. So let us take the example. So the sensitivity of a spring balance can be expressed as 25 mm per kg. That means 25 when 1 kg cause an additional displacement of the spring by 25 mm. That is the meaning of 25 mm per kg displacement. Sensitivity of an instrument also vary with temperature or other external environmental factors. So let us see that. Suppose the sensitivity of the spring balance mentioned above is 25 mm per kg at 20 degrees Celsius and 27 mm per kg at 30 degrees Celsius. So when the temperature increases, the sensitivity also increased from 25 to 27. So we can see an increase of 2 mm per kg when the temperature rises from 20 to 30 degrees Celsius. That means there is a sensitivity drift. Sensitivity of the amount has drifted by an amount 2 mm per kg per degree Celsius. That is 2 mm per kg per degree Celsius. So that is the sensitivity of the instrument drifted. That is called a sensitivity drift. So depending upon the measuring conditions, environmental conditions, locations of measurement, sensitivity may drift. So in order to avoid, so such drift is not desirable. So for a proper measurement we have to avoid such drift. So in order to avoid such drift sensitivity, Sophisticated instruments are either kept at controlled temperature or suitable inbuilt temperature compensation schemes are provided inside the instrument. So that is why when we are using some instruments, we have to go to the room or the space where the instrument is kept and we have to take the reading there, because that particular space is maintained for that particular instrument. So if we take that instrument out of that particular room, what will happen is this kind of errors will come into picture. So that is why some of the instruments, sophisticated instruments, are kept at some desirable temperatures. Then the sensitivity of the measurement. So that is now we have discussed about sensitivity of the instrument. So next is sensitivity of the measurement. That is again another type. The sensitivity of the measurement is a measure of the change in instrument output that occurs when the quantity being measured changes by a given amount. That is scale of deflection divided by value of the measurement producing deflection. Let us also see this as an example. So this is the sensitivity of the measurement. The first one was sensitivity of the instrument. So let us see what is sensitivity of the measurement by an example. So if we are taking a pressure gauge which measures a pressure of 2 bar, produces a deflection of 10 degrees in a pressure gauge. Sensitivity of the instrument is 5 degrees per bar, assuming that the deflection is 0 with a 0 pressure applied. So here a pressure of 2 bar produces a deflection of 10 degrees in a pressure gauge. Sensitivity of the instrument is 5 degrees per bar. That is, sensitivity of the instrument is a ratio of the change produced in the instrument output to the change in the measured value. So we can also define sensitivity in this way. That is delta Q0 divided by delta Qi. So Q0 is the output produced and Qi is the input given. So that is slope of output to input graph. If we take the slope of the output versus input graph, we will get the sensitivity value. Then next one is threshold. So if the input to an instrument is gradually increased from 0, the input will have to reach a certain minimum level before changing the instrument's output reading. This minimum level of input is known as threshold of the instrument. That is, when we are giving an input to a particular instrument, we will observe that there will be no output till the input has reached some values, some particular value. So up to that particular value, there will not be any output. So that is what is called threshold limit of the instrument. So for example, eddy current speedometer used in automobiles. So you can observe this threshold in that, because only after reaching a certain input value, we will observe an output reading. That is, the instrument has some threshold limit. So this is the minimum value of input below which no output can be appeared is known as threshold of the instrument. So we can see this with the help of a graph. So output versus input graph. On x-axis input is plotted, on y-axis output is plotted, and we can see here you can see that you observe here, you can see here you can see the arrow marked region where I am marked it with red pointer. You can see there is no output up to the marked region. So only when the input has increased beyond that marked region, the output appears on the instrument. So that is what is threshold. So now let us move to the next one, that is resolution. So if the input is slowly increased from some arbitrary input value, it will again be found that output does not change at all until a certain increment is exceeded. This increment is called resolution. So if we are measuring some input, or if you are increasing some input from some arbitrary input value, you have some arbitrary input value which is kept as a reference. We are increasing the input from that particular arbitrary value. Here also we will observe that there will be output only when the input has reached a certain limit. That is called resolution. Example, again, a voltmeter operating in 0 to 2 volt range can have a maximum reading of 1.999 volt. So 1.99 volt is kept as a reference value, and if there is a change in voltage below 0.001 volt, the instrument or the voltmeter will not show any reading, because that is the resolution of that particular instrument. So 1.99 volt is kept as a reference value, and the voltage is increased or decreased by an amount below 0.001 volt. We will observe that 0.001 volt will not be displayed in the voltmeter, so that change will not be detected by the voltmeter. That is resolution. So that is another characteristic. The resolution indicates a minimum change in input variable that is detectable. That is the definition. So it is also defined in terms of percentage, that is delta I divided by delta I max. That is the maximum current, minimum current. That is delta I is the change in current, delta I max is the maximum current, minimum current into 100. That's the equation for getting the resolution of any instrument. The next one is hysteresis. There is also another important feature or another important thing which is there in almost all measuring instruments which has got moving parts or which has got some electrical parts. So let us see what is hysteresis. So here you can figure shows illustrate the output characteristics of an instrument that exhibit the hysteresis. The input measured quantity to the instrument is steadily increased from a negative value. The output reading varies in a manner shown in curve A. So we have two curves here, curve A and curve B. So we have a reading on the negative side and we have a reading on the positive side. So the input, some input is increased from negative value, the output varies in a manner as shown in curve A. That is the curve or reading in the output of the instrument when the input is varied. That is shown by curve A. That is variable is increasing. So if the input variable is then steadily decreased, the output varies in a manner as shown in curve B. The non-coincidence between these loading and unloading curve is known as hysteresis. Now we have increased the input and reached the end of the curve A. Then we will decrease the input. Then we will see that the output follows the curve B. Instead of following the curve A, output follows the curve B. So curve B and curve A is at some space apart. So that is what is the phenomenon called hysteresis. Hysteresis is most commonly found in instruments that contain springs such as passive pressure gauge. So that is one of the phenomenon which is there in instruments which contain springs. That is a type of loss. Instrument was supposed to follow the curve A during loading and unloading, but that was not happened. During loading, instrument or output followed the curve A, but during the unloading, the output followed the curve B. So there is some difference between the output of the instrument during unloading and loading. That is termed as hysteresis. This type of loss or this type of problem is found in measuring instruments. So here x-axis is measured variable and y-axis is output reading. Curve is the output reading when the input is increased, and curve B is the output reading when the input is decreased. Same input is decreased, and that is we can see the maximum output hysteresis, maximum input hysteresis. All these things are shown. So the hysteresis is that particular phenomenon is called hysteresis. Then dead space or dead zone, that is another characteristics. Here we can see dead space is defined as a range of different input values over which there is no change in input value. Here you can see Again, the x-axis it is measured variable or variable to be measured, on y-axis output reading. Here we can see that only when the measured variable, you can see from the figure I will show you. Here you can see a gap that is which is marked as dead space. That is, the gap is marked as dead space. So during that dead space, there is some measured value changes there. So there is some input, but there is no output. So there is some input, but there is no output. That is known as dead space. So dead space is defined as a range of different input over which there is no change in output value. Some instruments that do suffer from any significant hysteresis can still exhibit a dead space in their output characteristics. Example, backlash in gears is a typical cause of dead space and result in sort of instrument output characteristics shown in figure. Then next characteristic is drift. So the actual change in the measurement value when same characteristics is measured under similar conditions and same operator different instruments needs recalibration, or it is slow change if a metrological characteristic of a measuring instrument. So zero drift or bias. So drift is classified into two types: zero drift, and second one is sensitivity drift or span drift. Let's see what is zero drift. So it describes the effect where the zero reading of an instrument is modified by change in ambient conditions. This causes a constant error that is called system error that exists over a full range of measurement. So let us take an example. If someone of non-weight 70 kg were to get on the scale, the reading would be 71 kg. And if someone of non-weight 100 kg were to get on a scale, the reading would be 101 kg. So that is, the zero reading has drifted by 1 kg. That is, it's called zero drift. See, we can see from the graph. So pressure versus scale reading. So the rigid lines shows the characteristic to zero drift on the left side, and the dotted line shows the nominal characteristics without any zero drift. So during the zero drift, we can see that the zero reading has drifted by some amount. That is zero drift. That is example, we can see 70 kg has been shown as 71 kg and 100 kg has been shown as 101 kg, because that means the zero reading has been drifted by 1 kg. So the reference has been 1 kg in that case. That is zero drift. So here also another graph, right hand side you can see the blue color graph. Again also original calibration curve is the lower one, and the shifted calibration curve is the upper one. So you can see the zero drift. So it's a drift happened to the original calibration curve. So that is what is zero drift. Then next is sensitivity or span drift. It defines the amount by which an instrument's sensitivity of measurement varies as ambient conditions change. So how much sensitivity change has happened when the ambient measurement conditions has changed. That is span drift or sensitivity drift. It is quantified by sensitivity drift coefficients that define how much drift there is for a unit change in each environmental parameter that the instrument characteristics are sensitive to. So every instrument characteristics are sensitive to some environmental parameters. So the sensitivity drift is quantified by sensitivity drift coefficients. So that is dependent upon each environmental parameter that a particular instrument characteristics is sensitive to. Many components within an instrument are affected by environmental fluctuations such as temperature changes. Example, the modulus of velocity may get affected by the change in temperature. The spring modulus of velocity of the spring, which is used as a basic component of almost all mechanical measuring devices. So when the modulus velocity of the spring changes, that causes sensitivity drift of the instrument. Here again we can see the example graph showing the sensitivity drift. We have the pressure on the x-axis and scale reading on the y-axis. So if we are starting from 0, we can see that the rigid line shows us characteristics of the sensitivity drift. The sensitivity of the instrument has changed due to some change in ambient conditions. The nominal characteristics must stop in the dotted line, but due to some change in environmental characteristic, the instrument was sensitive to the original curve as drifted. That is called sensitivity drift. The next one is zonal drift. So as the name indicates, it applies to only a particular specific zone of the measurement range. It is not happening all over the measurement, so it is only limited to a particular zone of the measurement region. That is, in case of drift occurs only a portion of the span of the instrument, it is called zonal drift. So that is zonal drift. So these are the characteristics of measuring instruments. So it's very important to control these performance characteristics of measurement instruments